For nearly a century, cosmology has described a universe born in fire, expanding through space and time, dominated by unseen components. The lambda CDM model has been extraordinarily successful, but every model rests on assumptions. What if cosmic redshift has another origin? What if time itself is not what we think it is? This is the Exochronous Universe, rethinking cosmology from first principles. Modern cosmology rests upon one of the most important observations in all of science. The light from distant galaxies appears shifted toward longer wavelengths, toward the red end of the spectrum. This phenomenon is known as redshift. From it we infer the expansion of the universe, the history of cosmic evolution, even the origin of space and time themselves. But what exactly are we observing? What does redshift truly mean? And how much of modern cosmology depends not only on observation, but on interpretation? To understand redshift, we first need to understand how astronomers study light itself. Light may appear continuous to the human eye, but when separated into its component wavelengths, it reveals hidden structure. Every chemical element absorbs and emits light at very precise wavelengths. Hydrogen, helium, oxygen, carbon, each leaves behind a unique spectral signature, like fingerprints embedded in light. When astronomers observe a distant galaxy, they compare these known spectral patterns against the light they actually receive, and what they find is that the patterns are often displaced. The spectral lines appear shifted toward longer wavelengths. This shift is quantified using a parameter called redshift, denoted by the symbol Z. Importantly, astronomers are not directly observing redness. They are measuring the displacement of precise spectral lines. There are basically three types of redshift. The first kind of redshift is familiar from everyday life, the Doppler effect. When an ambulance passes by, the pitch of its siren changes as it moves relative to the listener. Light behaves similarly. If a luminous object moves away from an observer through space, its wavelengths appear stretched. In this interpretation, redshift arises from relative motion. The source moves away, and the light shifts accordingly. But motion is not the only mechanism capable of shifting light. According to general relativity, gravity itself can alter wavelength. As light climbs out of a gravitational field, its frequency decreases, its wavelength increases. The light becomes redshifted. Gravitational redshift has been experimentally confirmed many times. Here, no recession through space is required. Space-time geometry alone is sufficient to alter the observed wavelength. The third form of redshift is the foundation of modern cosmology: cosmological redshift. In the standard model of the universe, space itself expands over time. As light travels across this evolving geometry, its wavelength stretches along with space-time itself. In this framework, redshift reflects the changing cosmic scale factor. The larger the shift, the more the universe is inferred to have expanded during the light's journey. Although Doppler and cosmological redshift may appear superficially similar, conceptually they are very different. One describes motion through space, the other describes the evolution of space itself. In the early 20th century, astronomers began measuring redshifts in distant galaxies. Vesto Slipher first observed that many galaxies appeared redshifted. Edwin Hubble later combined these measurements with estimates of galactic distance and discovered something remarkable. The farther away a galaxy appeared to be, the greater its redshift. This relationship became known as Hubble's law, and it transformed cosmology. The universe no longer appeared static. Instead, it seemed dynamic, evolving, expanding. Over time, the interpretation of cosmological redshift as expanding space became the central foundation of the modern cosmological model. But here we encounter an important distinction. Telescopes do not directly observe expanding space. They observe light. More specifically, they observe displaced spectral lines. From these measurements, cosmologists infer recession velocities, cosmic expansion, and the evolving geometry of spacetime itself. None of this makes the interpretation arbitrary. Modern cosmology rests upon an extraordinarily successful theoretical framework. But it does remind us of something important. Observation and interpretation are not identical. The redshift itself is directly observed. The physical mechanism responsible for it must be inferred through theory. Throughout the history of cosmology, physicists have explored many possible explanations for cosmic redshift: relative motion, gravity, expanding spacetime, and historically, even the possibility that light itself might gradually change during its journey across the cosmos. Most such tired light ideas failed important observational tests, and none replaced the standard cosmological model. But the deeper scientific question remains profoundly important. What physical process ultimately causes the observed shift in wavelength? We need to ask this question because every cosmological model rests upon deeper assumptions about spacetime, about distance, about clocks, and about how physical systems evolve across the universe. For nearly a century, cosmological redshift has been interpreted as evidence that the universe itself is expanding. And within modern cosmology, that interpretation has proven remarkably powerful. But as new observational tensions continue to emerge, some physicists have begun revisiting an older and deeper question. Are we observing expansion directly, or are we observing light and interpreting its meaning through a particular model of reality? In the next episode, we will explore what it truly means to say that space itself expands.